Hello, travelers. Welcome back to the Midnight Explorer. Close your eyes for just a moment. Let your breathing slow. Feel the weight of the day begin to lift from your shoulders. Tonight, we're going somewhere extraordinary. Somewhere that has called to humanity since the very first human looked up at the night sky and wondered. Tonight, we're going to explore the cosmos. Not as scientists in a laboratory, not as astronauts in a spacecraft, but as dreamers, as wanderers, as the same curious children who have always gazed upward and asked the eternal question, what is out there? This is not just a story about stars and planets. This is a story about us, about every human who ever lived, who ever looked up, who ever wondered if they were alone in the vast, infinite darkness. So settle in, pull your blanket a little closer. Let the worries of your day drift away like autumn leaves on a gentle stream. Because tonight, we are going to travel billions of years into the past. We're going to stand beside the first humans who named the constellations. We're going to feel what they felt, wonder what they wondered, and discover how their questions became our answers. This is the story of the cosmos. But more than that, it's the story of how we learn to read the universe like a book written in light. Are you ready? Then let's begin. Picture this with me. It's 40,000 years ago, maybe more. Time has a different meaning when you go back this far. The numbers become so large they stop making sense, so instead, just imagine a very long time ago. You're sitting beside a fire. Not a bonfire at a beach party, not a campfire at a summer camp. This is a survival fire, the kind that keeps the darkness at bay, the kind that stands between your small tribe and the unknown dangers that prowl in the night. The flames dance and pop. Sparks spiral upward into the darkness, little orange stars that fade and die before they reach the treetops. The heat feels good on your face. Your stomach is full. Tonight's hunt was successful. The meat still sits heavy and warm inside you. Your children are already asleep, curled against their mother beneath a shelter of branches and animal hides. The elder of your tribe, a man so old his face looks like cracked earth, sits across from you, staring into the flames. But you don't look at the fire. You look up. The sky above you is nothing like the sky you know in your modern life. There are no streetlights washing out the stars, no cities glowing on the horizon, no airplanes blinking their way across the darkness, no satellites, no light pollution. What you see is what humans saw for hundreds of thousands of years. What your ancestors saw, what the very first humans to be called human saw. And it is breathtaking. The Milky Way stretches across the heavens like a river of light, not a faint smudge you have to squint to see, but a brilliant, luminous band that cuts the sky in half. You can see its texture, its depth. Millions upon millions of stars packed so densely they blur together into flowing streams of silver light. Individual stars shine with a brightness that seems impossible. They don't just twinkle, they pulse, they breathe. Some are pure white, like holes punched in the fabric of night itself. Others have the faintest hint of color: blue, red, gold. You know these stars. Not their names. Names haven't been invented yet. But you know them the way you know your own children. You've watched them every night of your life. You've seen them wheel slowly across the sky as the seasons change. You've noticed that some stars move together in patterns, like hunters stalking prey across the heavens. Your people have stories about these patterns. The elder tells them sometimes when the fire burns low and sleep is still far away. Stories about great bears and mighty hunters. Stories about gods and monsters. Stories that explain why the stars move the way they do, why the moon grows fat and thin, why the sun travels its endless path across the sky. But tonight, as you stare up at that infinite darkness, a different feeling washes over you. Not comfort, not familiarity. Smallness. For the first time in your life, you truly feel how tiny you are, how brief. You are a single spark from the fire, spiraling up into darkness and gone before anyone can blink. Your entire life, everything you've ever done or will do, is less than a single breath in the life of those stars. The feeling should be terrifying, but somehow it's not. There's something beautiful about it, something peaceful. You are small, yes, but you are part of this, part of the night, part of the stars, part of whatever vast, unknowable thing this all is. You don't have words for this feeling. Your language is simple, made for simple things: hunt, fire, danger, sleep. But the feeling is there, sitting in your chest like a stone warmed by the sun. You are the first philosopher. You don't know it, but in this moment you're asking the same questions that will echo through all human history. Questions that will build telescopes and launch rockets. Questions that will inspire poetry and art and music. Questions that will never ever be fully answered. What is this? How far does it go? Am I alone? The fire pops. A log shifts, sending up a fresh spiral of sparks. The elder looks at you across the flames, and you wonder if he's asking the same questions, if he feels the same smallness, the same strange peace. But you don't speak. You just look up at the stars, and they look back at you, silent and eternal, keeping their secrets. This is where it begins. Not in a laboratory, not in a university, but here, in the darkness, beside a fire, with a human who didn't know they were making history simply by looking up and wondering.
Now we move forward through time. Not 40,000 years forward. We don't travel that far yet. Just a few dozen millennia. A blink in cosmic time. But long enough for humanity to change in ways that first fire-gazer could never imagine. We're in Mesopotamia now, the land between two rivers, the cradle of civilization, they'll call it later. But right now, in this moment, around 5,000 years ago, it's simply home to some of the first cities humans ever built. Picture Uruk, Babylon, cities of mud brick and ambition rising from the desert like monuments to humanity's growing confidence. We've learned to farm, to write, to organize ourselves into kingdoms and empires. We've gone from small tribes huddled around fires to civilizations of thousands. But we haven't stopped looking up. If anything, we look up more than ever. You're standing on a ziggurat now, a massive stepped pyramid of brick climbing toward the sky like a stairway built for gods. The sun is just set, painting the western horizon in shades of orange and deep purple. The heat of the day still radiates from the stones beneath your feet. You're a priest, an astronomer priest, though you wouldn't separate those two things the way later generations will. The sky isn't just something to observe, it's divine. Every star is a god or the servant of a god. Every movement in the heavens has meaning, carries messages from the realm of the immortals to the realm of mortals. Your people have been watching the sky for generations now. Not just watching, recording. You have clay tablets covered in cuneiform, recording the positions of stars, the movements of planets, the phases of the moon. This isn't idle curiosity. This is sacred duty. Because you've noticed something extraordinary. The sky is not chaos. The sky is order. The stars wheel across the heavens in perfect, predictable patterns. Night after night, season after season, year after year, they trace the same paths. The same constellations rise in the east, arc across the sky, set in the west. The moon follows a rhythm you can count on: new moon, crescent, half, full, half, crescent, dark. 29 days, over and over, reliable as breathing. Even the sun obeys rules. In summer, it rises far to the north, climbs high in the sky, makes the days long and hot. In winter, it rises far to the south, barely clears the horizon, makes the days short and cold. But every year it turns around at exactly the same place. You can mark the solstices with perfect accuracy. And then there are the wanderers. Most stars stay fixed in their patterns, but a few, 5 bright ones, move differently. They wander among the constellations like travelers on a road. Sometimes they move one direction, sometimes they stop, sometimes they move backward. Your people call them planets, from an old word meaning wanderer. You've spent your entire life learning their patterns: when Venus appears as the morning star, when Mars grows bright and red, when Jupiter and Saturn move into alignment. Every position, every combination has meaning. They speak of war and peace, harvest and famine, the favor or anger of the gods. This isn't superstition, or at least it's not just superstition. You're creating something new, something that has never existed before. You're creating science. You don't call it that. You don't think of it that way. But that's what it is. You observe. You record. You look for patterns. You make predictions. When Saturn appears in this constellation, the rains come late. When Venus rises with the sun during this month, the harvest is good. Sometimes you're right. Sometimes you're wrong. But you keep watching. Keep recording. Keep refining your predictions. You're learning to read the book of the sky. And here's what makes this moment so profound, so touching. You're doing it with tools that would seem laughably primitive to later generations. No telescopes, no computers, no cameras. Just your eyes, your memory, your clay tablets. But your eyes are enough. On a clear night, you can see about 3,000 stars. You learn to know them individually. This bright one is Sirius. That red one is Betelgeuse. That cluster is the Pleiades. You learn their stories, their names, their relationships to each other. You notice details that will astound later astronomers. You see that the North Star isn't quite north anymore. It's drifted slightly from where your grandparents said it was. You don't know about the precession of the equinoxes, don't understand that Earth wobbles on its axis over thousands of years, but you notice. You record it. You see that eclipses follow patterns, not random terrors sent by angry gods, but predictable events that occur in cycles. You can't predict them perfectly, not yet, but you can predict them approximately. You can warn people, look, when the moon reaches this point and the sun is here, darkness may fall in the day. The night deepens around you. The ziggurat is silent except for the wind. Below, the city sleeps. But you stand here on top of this massive pyramid of brick, suspended between earth and sky, recording the dance of the cosmos. You feel connected to something vast, something eternal. The gods speak through the stars, yes, but maybe, and this thought comes to you so quietly you almost don't notice it, maybe the stars speak for themselves. Maybe their movements are a language you're only beginning to understand. You think of the priests that came before you, your teacher who taught you to read the star tablets, your teacher's teacher who first began recording the planets, and all the ones before them, going back generations, each one adding a little more knowledge, a little more understanding. You think of the priests who will come after you, your students already learning to read the heavens, their students, and all the ones who will follow for generations you can't imagine. You're part of a chain, a succession of watchers passing the knowledge forward through time. You're not just observing the cosmos, you're building something, a foundation, a beginning. You don't know it yet, But your clay tablets will survive for thousands of years. Archaeologists will dig them up, dusty and broken, and gasp at their sophistication. Your observations of Venus will be so accurate that they can be used to date ancient events. Your star catalogs will influence civilizations you never dreamed existed. But right now, you're just a person on a ziggurat, looking up at the stars, trying to understand. And the stars look back, patient and eternal, keeping their secrets a little while longer.
Now we move to the shores of the Aegean Sea. The sun is warm here. The water is impossibly blue. White stone temples gleam on hilltops. This is ancient Greece, around 2,500 years ago, and something extraordinary is happening. People are still watching the sky, but now they're asking a new kind of question. Not just, what are the stars doing, but why? You're walking through Athens on a pleasant afternoon. The marketplace buzzes with life. Merchants selling figs and olive oil, philosophers debating in the shade of colonnades, students hurrying to their lessons. The air smells of bread baking and sea salt. You're going to hear a lecture by a philosopher named Anaxagoras. He's famous, controversial. Some people say he's brilliant. Others say he's dangerous. He was nearly executed a few years ago for his ideas about the cosmos. You find him in a garden, surrounded by young students sitting on the ground. He's old now, his beard long and gray, but his eyes are bright with the fire of ideas. The sun, he's saying, is not a god. It's a stone, a burning stone larger than the Peloponnese. Gasps from some of the younger students. One boy looks terrified, glancing around as if expecting lightning to strike. But Anaxagoras continues calmly. The moon is not a goddess. It's an earth, like our earth, with mountains and valleys. It doesn't shine with its own light. It reflects the light of the sun. And the stars? They're suns themselves. So far away they appear as points of light. You feel a shiver run down your spine. Not from fear, but from something else. Something like vertigo. Because if what this old man is saying is true, then the cosmos is not what you thought it was. It's not a dome painted with lights. It's not the floor of heaven close enough to touch if you climbed high enough. It's vast, incomprehensibly vast. The stars aren't just far away. They're so far away that human words struggle to describe it. And if each star is a sun like our sun, then what about the space between them? What fills that imaginable distance? How do you know this? A student asks, voice trembling slightly. Anaxagoras smiles. I observe. I reason. Watch a lunar eclipse. You see Earth's shadow on the moon, curved, proving our world is round. Watch a solar eclipse. The moon passes in front of the sun, proving the moon is closer than the sun. Observe how distant mountains disappear bottom first over the horizon. Everything we see confirms it. This is revolutionary. Before this moment, humans had stories about the cosmos. Beautiful stories, sacred stories. But Anaxagoras and philosophers like him are doing something different. They're using reason, logic, observation. They're trying to understand the cosmos not through mythology, but through natural law. Let's move now to another part of Greece, the island of Samos. We're visiting a man named Aristarchus, and he's about to propose something so radical it will be rejected for nearly 2,000 years. Picture him in his study, surrounded by scrolls and astronomical instruments. He's been measuring the angles between the sun and moon during its quarter phases. He's been calculating, using geometry that would impress mathematicians today. And he's reached a stunning conclusion. The Earth, he says quietly to his students, moves around the sun, not the other way around. The Earth is not the center of the cosmos. The sun is the center. We orbit it, like the other planets. And the stars don't revolve around us at all. They're impossibly distant, and they only appear to move because our Earth spins on its axis. One student finds his voice. But we don't feel the Earth moving. Of course not, Aristarchus replies patiently. If you're on a smoothly sailing ship, you don't feel the motion either. The Earth is so large, its motion so smooth, we're carried along without sensation. But if the Earth moves around the sun, we should see the stars shift position as we orbit. We should see parallax. Yes, Aristarchus nods. Which means the stars must be so far away that the parallax is too small for us to measure. Imagine how distant they must be for that to be true. He's right, absolutely right. But his idea is too radical, too counterintuitive. It will be forgotten, buried in the dusty scrolls of history, waiting nearly 1,800 years for Copernicus to rediscover it. But right now, in this moment, this Greek philosopher has glimpsed the truth. The Earth is not the center of everything. We're one planet among many, orbiting a sun that's one star among countless billions. We're adrift in an ocean of space so vast that human imagination strains to conceive it. You leave the lecture as the sun sets over the Aegean Sea. Your mind is reeling. You walk to the shore and sit on the rocks, watching the waves roll in, feeling the solid stone beneath you. The Earth moves. The sun is just another star. The cosmos is vast beyond comprehension. Everything you thought you knew about your place in the universe has been turned upside down. But here's what strikes you as you sit there, watching the first stars appear in the deepening blue. This feels right. Frightening, yes. Humbling, absolutely. But somehow it feels right. Because a cosmos this vast, this ancient, this filled with light and mystery, that's a cosmos worthy of wonder. That's a cosmos big enough to hold all your questions, all your dreams, all your desperate human need to understand. The waves keep rolling in, the stars keep appearing one by one, like flowers blooming in a garden of night. And you sit there, a small human on a spinning planet orbiting an ordinary star in a universe too large to imagine, and you feel strangely at peace. Because for the first time, you understand you don't need to be the center of everything to matter. You don't need the cosmos to revolve around you for your life to have meaning. You're part of something bigger, something magnificent, something that was ancient before you were born and will continue long after you're gone. And that, somehow, is enough.
Now, we must travel through time differently, not forward by centuries, but forward by more than 1,000 years. And this journey, this long leap, is different from the others, because these 1,000 years are, in many ways, lost years for the understanding of the cosmos. The Roman Empire has fallen, the great libraries have burned, the philosophical schools have closed. Europe has descended into what later generations will call the Dark Ages, though that name isn't quite fair. There was still learning, still wisdom, but it had retreated, gone underground, flickered dimly in monastery scriptoriums and isolated courts. Let's visit one of these monasteries. Picture it with me. You're in a stone building so cold you can see your breath even in summer. The walls are thick, the windows narrow slits that let in grudging light. It's somewhere in what will become Germany, or maybe France. The borders shift so often in these troubled times that it's hard to say. You're a monk, a copyist. It's your sacred duty to preserve knowledge by copying books, letter by letter, word by word. Your fingers are stained with ink. They're also stiff and aching from the cold. Today, you're copying a manuscript about the cosmos. It's a Christian interpretation of Ptolemy's model of the heavens. The Earth at the center,
unmoving, the moon, sun, planets, and stars arranged in crystalline spheres around it. The whole cosmos small, contained, knowable. Heaven above, hell below, humanity in between. It's beautiful in its way. Orderly, comforting. Everything has its place, its purpose. The cosmos exists for humanity, and humanity exists for God. Simple, clean, complete. But sometimes, late at night, you remember fragments of the older texts, the Greek philosophers you've read in crumbling scrolls. Anaxagoras saying the sun was a burning stone. Aristarchus proposing that Earth moves around the sun. Heresy, of course, dangerous thoughts, the kind that could get you branded a heretic, stripped of your position, or worse. But you remember them anyway. You dip your quill in ink and continue copying. The words flow onto the parchment in careful Latin script. But your mind wanders to the window, to the thin shaft of sunlight slanting across your desk. A burning stone, Anaxagoras had said, larger than the Peloponnese. You shake your head and return to your copying. Some knowledge, you think, is meant to sleep for a while, waiting for a time when the world is ready to hear it again. But not all the knowledge was sleeping. Let's travel now, southeast, across the Mediterranean, to Baghdad. The year is around 850 CE, and while Europe struggles through its dark ages, the Islamic Golden Age is in full bloom. The House of Wisdom stands before you, a magnificent library and research center buzzing with scholars from across the known world. Muslims, Christians, Jews, pagans, all working together, translating, studying, discovering. You're in a room with a man named Al-Khwarizmi. He's bent over astronomical tables, calculating the positions of planets with astonishing precision. Around him are manuscripts in multiple languages: Greek, Sanskrit, Arabic. He's gathering all the astronomical knowledge of the ancient world, correcting it, improving it. He says, the Greeks were brilliant, but they made mistakes. Their measurements of the solar year were slightly off. Their planetary models didn't quite match observations. We can do better. And they do. The Islamic astronomers of this era make stunning advances. They build more accurate astrolabes. They create better star catalogs. They refine the mathematics of astronomy. They preserve and translate the Greek texts that Europe has lost. They keep the flame alive. In Persia, a scholar named Abd al-Rahman al-Sufi writes The Book of Fixed Stars, describing hundreds of stars with unprecedented accuracy. He's the first to record seeing the Andromeda galaxy, although he doesn't know that's what it is. He calls it a small cloud. In Cairo, the astronomer Ibn Yunus builds a massive astronomical instrument and uses it to compile tables that will be used for centuries. He measures the obliquity of the ecliptic. He refines the length of the solar year to within seconds of the modern value. These aren't just careful observers. They're asking new questions. They're developing new mathematics. They're building instruments that push the boundaries of what's possible with the naked eye. And crucially, they're keeping the ancient knowledge safe. When a young monk in a European monastery reads Aristotle or Ptolemy, he's usually reading a Latin translation of an Arabic translation. The Islamic scholars are the bridge, carrying the wisdom of the ancient world across the chasm of time. But even here, even among these brilliant minds, the cosmos remains small, contained. The stars are still thought to be fixed lights on a distant sphere. The Earth is still the center, unmoving. Some truths aren't ready to be reborn yet. Let's move forward again. We're in Italy now, a monastery garden in the 1300s. You're listening to a traveling scholar who's just returned from Spain, where Christian and Muslim scholars still sometimes meet and exchange ideas.
They have a name for the dark patch in the sky. They call it a nebula. They wonder if it might be a cloud of some substance between the stars. But there is nothing between the stars, another monk protests. The space beyond the moon is perfect, unchanging, made of quintessence, the fifth element. Perhaps, the traveler says carefully, but they have seen new stars appear, stars that weren't there before. If the heavens are unchanging, how can that be? The question hangs in the air, unanswered. Because that's what this long period is, a time of questions without answers, of knowledge preserved but not advanced, of careful observation that can't quite break free of ancient assumptions. But slowly, things are changing. Universities are being founded. Oxford, Paris, Padua, Bologna. Places where questions can be asked, where old texts can be studied, where new ideas can circulate. Carefully, always carefully, but they circulate. Translations are proliferating. The wisdom of the Greeks and the discoveries of the Islamic scholars are seeping back into Europe, filtering through Spain and Sicily, carried by Jewish translators who can read Arabic, Hebrew, Latin, and sometimes Greek. And somewhere, in all this slow movement of ideas across borders and centuries, something is building. A pressure, a tension, like water behind a dam. The old model of the cosmos, Earth at the center, everything else revolving around it, is becoming harder and harder to maintain. Astronomers have to add more and more complications to make it match observations. Epicycles upon epicycles, deference and equants. The elegant simplicity of the ancients has become a Baroque monstrosity. Something has to give. And soon, very soon, in the long calendar of human history, it will. But for now, in this monastery, in this moment, you're still copying manuscripts by candlelight, still preserving the old knowledge, still waiting, though you don't know you're waiting, for someone brave enough to ask the old questions in a new way. The candle flickers, your hand moves across the parchment, forming letters that will last centuries. Outside, the stars wheel through their ancient patterns, patient and eternal. The long sleep is almost over.
The year is 1543. We're in a small room in Frauenburg, in what is now Poland. An old man lies dying in a bed. His name is Nicholas Copernicus, and he's holding something he's waited his whole life to see. A book. His book. De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. It's just been delivered from the printer. He's barely conscious anymore, fading in and out. But someone places the fresh, crisp pages in his hands, and for a moment, his eyes open. He touches the paper, the ink, the diagrams he spent decades perfecting. He dies a few hours later. He doesn't know that his book is about to change everything. Let's step back a bit. Let's visit Copernicus 30 years earlier, when he's a younger man, working on these ideas in secret, afraid to publish them because he knows how revolutionary they are. He's sitting at his desk, surrounded by astronomical tables and calculations. The window is open to the summer night, and the stars are visible beyond. He's been working on a problem, the same problem that has troubled astronomers for centuries. The planetary motions don't make sense in the Earth-centered model. You have to keep adding complications, epicycles on epicycles, to make the mathematics work. It's ugly, inelegant, and Copernicus, who loves mathematics, who believes that the cosmos should be governed by beautiful, simple laws, can't accept it. So he tries something radical. He tries putting the sun at the center instead. At first, it's just an experiment, a thought exercise. What would happen if Aristarchus was right, if the Earth moved around the sun instead of the other way around? He does the mathematics, reworks the tables, recalculates everything. And slowly, His hands begin to shake. Because it works. It works beautifully. Suddenly, everything becomes simpler. The strange retrograde motions of the planets, the way they sometimes seem to move backward through the sky, aren't strange at all. They're just an optical illusion caused by Earth's own motion. Like watching another car on the highway. Sometimes it seems to move backward, even though both of you are moving forward. The epicycles fall away. The calculations become elegant, simple, the kind of mathematics that feels true in your bones. But this simplicity comes at a terrible price. The Earth is not the center of everything. The Earth moves. Humanity is not the axis around which the cosmos revolves. Copernicus stares at his calculations, feeling a mix of exhilaration and terror. He's right. He knows he's right. The mathematics is too beautiful to be wrong. But to say this publicly, to contradict Aristotle, Ptolemy, the Bible, 1,500 years of Christian teaching? He could be branded a heretic, lose his position, his reputation, maybe his life. So he keeps his work secret, shows it only to trusted friends, continues his day job as a church administrator while nursing this dangerous truth in private. But secrets like this don't stay secret. Word spreads through the network of scholars. A mathematician in Rome hears about it, an astronomer in Germany, a young professor in Wittenberg. They write letters, begging Copernicus to publish. The world needs to know this. Finally, in his old age, he relents. He lets a young mathematician named Rheticus prepare his manuscript for publication. But even then, he hedges. The book includes a preface, written without his knowledge by a nervous publisher, suggesting that the sun-centered model is just a mathematical convenience, not a literal truth. Copernicus, if he ever read that preface, must have been furious. But by the time the book reached him, he was dying, and so his revolution enters the world on uncertain peat, claiming to be less than it is. But the truth has a way of asserting itself. Let's jump forward now. 50 years. We're in Prague, in the court of the Holy Roman Emperor. It's a strange place, this court. Part scientific academy, part alchemical laboratory, part imperial palace. The emperor, Rudolph II, is obsessed with the mysteries of nature, collecting scholars and mystics and scientists with equal enthusiasm. And in this strange place, we find two men about to change everything. The first is Tycho Brahe, the greatest observational astronomer of his age. He's a colorful character, Tycho. He has a metal nose, lost the original in a sword duel over a mathematical formula. He keeps a tame elk as a pet. He built his own island observatory and filled it with the most advanced astronomical instruments in the world. For 40 years, Tycho has been observing the heavens with unprecedented precision. He's measured the positions of stars and planets with accuracy that won't be surpassed for centuries. He's seen a new star appear in the supposedly unchanging heavens, a supernova, though he doesn't know that word. He's tracked a comet's path and proved it must be moving through the realm of the planets, not Earth's atmosphere as Aristotle claimed. The unchanging heavens are changing. The perfect celestial spheres don't exist. The old model is crumbling. But Tycho can't quite accept Copernicus's solution. The Earth moving? It seems absurd. So he develops his own compromise model. The sun orbits Earth, but everything else orbits the sun. It's awkward, but it preserves the Earth's special position. Enter the second man, Johannes Kepler. He's younger than Tycho, poorer, from a lower social class, but he has something Tycho lacks, a fierce belief in the Copernican model and the mathematical genius to prove it. Tycho hires Kepler as an assistant. It's a tense relationship. Tycho hoards his precious data, doling it out in small pieces, afraid that Kepler will outshine him. Kepler, desperate for the data he needs, plays the patient assistant while seething with frustration. Then suddenly Tycho dies, possibly mercury poisoning, possibly a burst bladder from holding his urine too long at a feast. He was too polite to leave the emperor's table. History isn't sure. But in death, Tycho gives Kepler the greatest gift imaginable, access to 40 years of the best astronomical observations ever recorded. Kepler dives into the data like a man possessed. He's trying to calculate Mars's orbit, and, according to both the old Earth-centered model and the new Sun-centered model, Mars should move in circular paths. Circles are perfect. The heavens must use perfect shapes. But the data don't fit circles. No matter how many epicycles he adds, no matter how he adjusts his calculations, Mars refuses to cooperate. The observations are off by just 8 minutes of arc, about a quarter of the width of the full moon. A lesser astronomer would have dismissed this tiny discrepancy, assumed Tycho made a measurement error. But Kepler trusts Tycho's observations, and he trusts mathematics more than he trusts ancient assumptions about perfection. So, he tries something radical. What if the orbits aren't circles? He tries ovals. Close, but not quite right. He tries egg shapes. Closer. And then one day he tries an ellipse. A perfect mathematical curve, but not a circle. Slightly elongated, with the sun at one focus of the ellipse, not the center. The data fits. Perfectly. Kepler sits back, staring at his calculations. His hands are shaking again, that same shake Copernicus felt decades earlier. The shake of someone who has just seen past the veil of appearances to the truth beneath. The planets don't orbit in circles. They orbit in ellipses. This doesn't seem like much, does it? Just a small change in shape. But it's everything. Because it means the heavens aren't perfect in the way the ancients imagined. They're not built from ideal Platonic forms. They're built from mathematical relationships. Real, natural, beautiful relationships. But not the crystalline perfection philosophers had imagined for 2,000 years. Kepler keeps working. He discovers more laws. The planets don't move at constant speeds. They speed up when they're closer to the sun, slow down when they're farther away. And there's a mathematical relationship between how long a planet takes to orbit and how far it is from the sun. These are Kepler's laws of planetary motion. They describe exactly, precisely, how the planets move. Not approximately, not close enough for government work. Exactly. But even Kepler doesn't fully understand what he's found. He thinks there must be some force pushing the planets along, like angels guiding them. He spends years trying to find mystical musical relationships in the orbits, the music of the spheres made mathematical. It will take another genius to understand what Kepler has really discovered. But that genius is already born. A baby, nursing at his mother's breast in England, unaware that he will someday explain why planets move the way Kepler described. His name is Isaac Newton. But we're not ready for Newton yet. First, we need to meet someone else. Someone who will shatter the ancient cosmos in a different way. His name is Galileo Galilei.
It's a warm evening in Padua, Italy. The year is 1609. You're standing in a courtyard outside a house, part of a small crowd of curious onlookers. Everyone is buzzing with excitement and skepticism in equal measure. Inside the house, Galileo Galilei is preparing to demonstrate something extraordinary. You've heard the rumors, of course. A Dutch spectacle maker has created a device, a tube with lenses, that makes distant objects appear closer. A toy, really. A novelty. But somehow, word of it reached Galileo, and he's done something unexpected. He's improved it, dramatically. And now he claims he's going to show you things in the heavens that no human has ever seen. The man himself emerges from the house. He's middle-aged, stocky, with a reddish beard and bright, intelligent eyes that seem to miss nothing. He's carrying a tube about 3 feet long, made of wood and leather, with glass lenses at each end. "My telescope," he announces proudly. There's a slight lisp to his speech, but his voice carries confidence. "Magnification of 20 times. I point it at the sky, and I see what has been hidden since the beginning of time." Skeptical murmurs from the crowd. The moon is rising, bright and gibbous, about 3/4 full, Galileo points his tube at it. "Here," he says, offering the telescope to you. "Look!" You put your eye to the small end of the tube. At first, you see nothing but darkness. You adjust, moving your head slightly, and suddenly, you gasp. The moon fills your vision. Not the smooth, perfect sphere you've always seen. Not the flawless celestial object of Aristotle's philosophy. It's rough, cratered. You can see mountains, actual mountains, casting shadows across vast plains. You can see valleys, craters. The Terminator line between day and night isn't smooth. It's jagged with peaks, catching the sunlight while their valleys still lie in darkness. The moon isn't a perfect celestial sphere. It's a world, a place, somewhere with geography, with terrain, with features you could map if you had time and patience. Your hands start to tremble. You pull away from the telescope, blinking, trying to process what you've just seen. The heavens, Galileo says quietly, are not perfect. They're not fundamentally different from Earth. The moon is made of the same kind of material as our world. Mountains, plains, probably rocks and dust. Over the next few months, Galileo will continue his observations, and each one will be more shocking than the last. He'll point his telescope at Jupiter and see 4 small stars arranged in a line near the planet. The next night, they'll have moved. And the night after that. He'll realize with mounting excitement that these aren't stars at all. They're moons. Moons orbiting Jupiter, just like our moon orbits Earth. This discovery will shake the foundations of astronomy. Because if Jupiter has moons orbiting it, then Earth isn't the only center of motion in the universe. Things can orbit things other than Earth. The old certainty, everything orbits Earth, is shattered. He'll point his telescope at Venus and watch over months as it goes through phases, like the moon. Full, gibbous, quarter, crescent, new. This is only possible if Venus orbits the Sun, not Earth. It's direct visual evidence for the Copernican model. He'll look at the Milky Way and discover it's not a luminous cloud. It's stars. Thousands upon thousands of stars, too faint and too numerous to see individually with the naked eye, but revealed by the telescope in overwhelming profusion. He'll observe Saturn and see something strange. The planet seems to have handles or ears. His telescope isn't quite good enough to see Saturn's rings clearly, but he knows something odd is there. Something no ancient astronomer ever suspected. Each observation is a nail in the coffin of the old cosmos. The perfect, unchanging heavens don't exist. The Earth isn't the center of everything. There are more things in heaven than philosophy dreamed of. But let's skip forward now to a different moment, a darker one. It's 1633. You're in Rome, in a chamber of the Inquisition. Galileo stands before the cardinals, old now, sick, exhausted by months of interrogation and house arrest. He's being forced to recant, to deny what he's written, what he's seen, what he knows to be true. His book, Dialogue Concerning the Two Chief World Systems, has been banned. It defended the Copernican model too openly, too cleverly. The Church has decided this is heresy. One by one, the charges are read. Galileo has held and taught that the sun is the center of the world and does not move, that the earth is not the center and moves, that these positions are not merely hypothetical but true, that he has disobeyed the Church's order not to teach these doctrines. Galileo, kneeling, worn down by age and fear and the threat of torture, reads his recantation. His voice is barely audible. "I abjure, curse, and detest the said errors and heresies. I swear that in the future I will never again say or assert, verbally or in writing, anything that might cause a similar suspicion about me." Legend says that as he rose from his knees, he muttered under his breath, "E por si mueve," and yet it moves. Probably he didn't really say it. It's too perfect, too dramatic. The kind of thing we wish had happened rather than something that probably did. But whether he said it or not, it's true. The earth does move. The evidence is overwhelming. You can force a man to deny it. You can ban books, burn telescopes, threaten heretics with torture and death. But you can't stop the truth from eventually emerging. You can't unknow what has been learned. You can't unsee what has been seen. Galileo spends the rest of his life under house arrest. He goes blind, perhaps from all those hours looking at the sun through his telescope, trying to observe sunspots. He continues working anyway, dictating his final book on the mathematics of motion. He dies in 1642, blind and confined, officially disgraced. But his observations live on. His books circulate in Protestant countries where the Inquisition has no power. His methods spread. Others build telescopes, make their own observations, confirm what Galileo saw. The old cosmos is dying. Not quickly. These things never happen quickly. There are still holdouts, still believers in the Earth-centered universe, still people who refuse to look through a telescope because they know they'll see things that contradict their certainties. But slowly, inevitably, the new cosmos is being born. A cosmos where Earth is not the center, where the heavens are not perfect, where there are more worlds than anyone imagined, where the universe is vastly larger than anyone dreamed. And yet, and this is crucial, it's a cosmos that follows laws, mathematical laws, laws that can be discovered, tested, understood, laws that work the same everywhere, from Earth to Jupiter to the most distant star. This is the gift Galileo gives us. Not just observations, though those are revolutionary, but a method, a way of learning. Observe nature directly, not through the filter of ancient authority. Use mathematics to describe what you see. Test your theories against evidence. This is science, modern science, and it's about to bear fruit beyond anyone's wildest imaginings. Because in England, a young man is sitting under an apple tree thinking about why things fall.
Picture a young man, barely 23 years old, sitting in a garden in Lincolnshire. It's 1666, the plague year. Cambridge University has closed to avoid the epidemic, so students and fellows have scattered to the countryside. This young man isn't particularly sociable. He's moody, intense, obsessive. He's been thinking about mathematics and natural philosophy with a focus that borders on mania. Days blur together. He forgets to eat. He's chasing something, some pattern he can sense, but can't quite grasp. His name is Isaac Newton, and he's about to have the most productive year any scientist has ever had. The apple story is probably apocryphal, or at least embellished, but something like it might have happened. He's sitting in the garden, and he sees an apple fall from a tree. A common enough sight. But Newton's mind works differently than most people's minds.
The apple falls down, always down, never sideways, never up. Why? There must be some force pulling it toward the earth. That much is obvious. People have known that since forever. Things fall. Heavy things seek the center of the earth. Basic stuff. But Newton thinks, what if it's not just the earth pulling the apple? What if the apple is also pulling the earth? Tiny, insignificant pull, but there nonetheless. And if every object pulls on every other object, then what about the moon? The moon is just falling, like the apple. It's trying to fall to Earth, but it's also moving sideways, so instead of falling down, it falls around. An orbit is just a continuous fall that never quite reaches the ground. And if that's true for the moon, it's true for the planets orbiting the sun. They're falling toward the sun, but moving sideways fast enough that they keep missing. Newton's hands start to shake, that same shake we've seen before. Copernicus, Kepler, Galileo. The shake of someone seeing through the veil of appearances to the machinery underneath. He starts calculating. If gravity is a universal force, if every object attracts every other object, then he can derive Kepler's laws mathematically. They're not separate observations that happen to be true. They're consequences of a deeper principle. The mathematics is ferociously difficult. Newton has to invent new mathematics to handle it, what we now call calculus. He works through the summer and fall, filling notebook after notebook with calculations. And when he's done, he has it. A single law, elegant and complete. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. That's it. One law. But from this one law, everything follows. Why apples fall, why the moon orbits Earth, why planets orbit the sun, why comets trace their long elliptical paths through the solar system, why tides rise and fall. All of it unified into one beautiful mathematical framework. But here's what makes Newton's achievement so profound, so reality-altering. He's shown that the same laws that govern earthly objects also govern celestial objects. There's no fundamental difference between the heavens and Earth. An apple falling in Lincolnshire and the moon orbiting Earth are doing the same thing, following the same law. The ancient division between the corrupt, changing terrestrial realm and the perfect, eternal celestial realm? Gone. The universe is one place, governed by one set of laws. Newton doesn't publish his work immediately. He's secretive by nature, suspicious of others stealing his ideas. He continues his research, expands his theories, but keeps them largely to himself. It's not until 1687, more than 20 years later, that he finally publishes Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The Principia, as it comes to be known. Let's visit that moment. You're in London, at a meeting of the Royal Society. The great minds of English science have gathered to hear Edmund Halley present Newton's work. Halley is the one who convinced Newton to publish, who paid for the printing himself because the Royal Society was broke. As Halley explains Newton's system, you watch the faces around the room. Confusion at first. The mathematics is difficult. Even brilliant mathematicians struggle with it. But slowly, understanding dawns. And with understanding comes awe. He's done it, someone whispers. He's actually done it. He's explained the system of the world. And he has. The Principia doesn't just explain how planets move, it explains tides by the moon's gravity. It explains the precession of the equinoxes by the sun and moon's gravitational pull on Earth's equatorial bulge. It explains why the Earth is slightly flattened at the poles. It predicts where comets will return. In one monumental work, Newton has turned the cosmos from a mysterious, divine clockwork into a vast machine
whose workings can be precisely calculated and predicted. If you know the position and velocity of every object at one moment, and you know the law of gravity, you can calculate where everything will be at any future moment. The universe becomes, in principle, predictable, deterministic, comprehensible. This is both exhilarating and, in a strange way, melancholy. Because there's less room for mystery now. Less room for the hand of God actively guiding planets along their paths, actively intervening in the workings of nature. The universe runs by law, like a perfect mechanism, and once set in motion, it needs no further intervention. Newton himself doesn't see it this way. He's deeply religious. He believes God created the laws and maintains the system, but others, in later generations, will use Newton's work to argue for a purely mechanistic clockwork universe that needs no divine involvement at all. But that's later. Right now, in this moment, what matters is the unification. The same force that makes an apple fall explains the motion of the moon. The laws that govern Earth govern the cosmos. We live not in separate realms, terrestrial and celestial, but in one universe, operating according to principles we can discover and understand. Let's jump ahead a bit. It's 1705. Edmund Halley has been studying comets using Newton's laws. Comets have always been terrifying omens, unpredictable harbingers of disaster, moving through the sky in defiance of all the neat categories astronomers have created. But Halley realizes that a comet that appeared in 1682 has a very similar path to comets that appeared in 1607 and 1531, about 76 years apart. What if they're not three different comets, but the same comet, returning? Using Newton's laws, Halley calculates the comet's orbit. It's a highly elliptical ellipse stretching far out beyond the planets and then swooping back toward the sun. If his calculations are correct, the comet should return in 1758. He makes a bold prediction. The comet will return. He won't live to see it, he'll be dead by then, but it will return, and its return will prove Newton's laws govern even these most unpredictable of celestial objects. December 1758. Halley has been dead for 16 years, but amateur astronomers across Europe are scanning the skies, searching for Halley's comet. And on Christmas night, a German farmer and amateur astronomer named Johann Georg Palitzke sees it. A faint smudge of light in the constellation of Pisces, exactly where Halley's calculations said it would be. The comet returns. Halley's comet, they call it now. And its return is more than just the return of a celestial body. It's the ultimate vindication of Newton's system. The universe is predictable, understandable, governed by mathematical law. You can imagine the feeling spreading through the scientific community, a sense of triumph, of power. We can predict the future movements of the heavens with precision. We understand how the universe works. But even as this confidence spreads, even as Newton's laws come to seem like the final word on the cosmos, nature is preparing surprises that will shake everything again. Because the universe is stranger than Newton imagined, stranger than anyone in the 18th century could conceive. And the next chapter of our story will take us to those strange discoveries, to the realization that the universe is not just larger than we thought, it's larger than we could possibly have imagined. We're in Bath, England now. It's a pleasant evening in March 1781. You're in the garden behind a townhouse, and above you, a man stands on a ladder, peering through the eyepiece of a telescope he built himself. His name is William Herschel, and by day he's a musician, an organist and composer. But by night, he's an obsessive astronomer, spending every clear evening systematically surveying the sky, recording every object he sees. Tonight, he notices something odd. A small disk that doesn't quite look like a star. It's tiny, but definitely extended, Stars are point sources, but this has a visible size through his telescope. "Caroline," he calls down to his sister, who serves as his assistant. "Come look at this." Caroline Herschel climbs the ladder. She's an astronomer in her own right, though the age doesn't quite recognize women as scientists yet. She'll discover several comets herself in the coming years, but tonight she's helping her brother. "What do you make of it?" William asks. Caroline studies the object. A comet, perhaps? But it's not moving like a comet, and there's no tail. Over the following weeks, Herschel tracks the object. It moves, but slowly, steadily, and then he performs the calculations that will make him famous. It's not a comet. It's a planet. A planet beyond Saturn. A planet unknown to the ancients, invisible to the naked eye. A planet that has been orbiting the sun since the beginning of time, and no human ever knew it existed until this moment. They'll eventually name it Uranus, after the Greek god of the sky. And its discovery will double the known size of the solar system at a stroke. Think about what this means. For all of human history, there were 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, Saturn. These were the wandering stars, known to every civilization that ever looked up. Fixed, complete, the full set. And now, suddenly, there's a 6th one, found not by divine revelation or ancient wisdom, but by a musician with a homemade telescope, systematically scanning the sky. If there's one planet beyond Saturn, might there be others? Where do the planets end? William Herschel becomes obsessed with an even deeper question. How far away are the stars? Everyone knows the stars are distant, but how distant? Are they just beyond the planets, or are they truly remote, separated from us by gulfs of space that dwarf the solar system? Herschel has an idea. If Earth orbits the sun, then stars should show parallax. They should shift position slightly as Earth moves from one side of its orbit to the other. The closer the star, the bigger the shift. Previous astronomers have looked for this parallax and failed to find it. Copernicus had predicted it, but it had never been observed, which was one argument against the Earth moving. If Earth orbits the sun, why don't we see parallax? The answer, Herschel suspects, is that the stars are so far away that the parallax is tiny, too small to measure with existing instruments. But what if you look at double stars, pairs of stars very close together in the sky? If one is much closer than the other, you should see them shift position relative to each other as Earth orbits. Herschel spends years observing double stars, and he makes a discovery, but not the one he expected. The double stars aren't optical illusions, one star close, one far, just happening to line up from our perspective. They're real pairs, binary stars, orbiting each other, bound together by gravity. This is profound. Newton's law of gravity doesn't just work in our solar system, it works everywhere. Stars across the vast gulf of space are pulling on each other, orbiting each other, following the same mathematical laws that govern the fall of an apple or the motion of the moon. The universe is unified not just between Earth and sky, but across the greatest distances imaginable. The laws of nature are truly universal. But Herschel hasn't measured stellar parallax. The stars remain defiantly fixed in their positions, refusing to show any shift as Earth orbits. How far away must they be for that to be true? Herschel does calculations, conservative ones.
The nearest stars must be at least hundreds of thousands of times farther than the Sun, more likely millions of times farther. The universe has suddenly become incomprehensibly vast. Not just the solar system, that's familiar now, mapped and measured, but the space between stars, the gulf that separates our sun from its nearest neighbors. Light travels fast, that's been measured, about 186,000 miles per second. It takes light just over 8 minutes to reach Earth from the sun. But from the nearest star? Years, many years. The light we see in the night sky aren't showing us the present. They're showing us the past. The light left those stars years ago, decades ago, maybe centuries ago. We're looking backward in time, just by looking up. Let's move forward now. It's 1838. We're in an observatory in Germany. Friedrich Bessel, one of the greatest observers of his age, has finally done it. He's measured stellar parallax. Using a telescope with unprecedented accuracy, observing the star 61 Cygni for over a year, measuring its position to fractions of an arcsecond, he's detected the tiny shift caused by Earth's orbital motion. The parallax is minuscule, about a third of an arcsecond, roughly the angle subtended by a coin viewed from 3 miles away. But it's there, measurable, real. And from that tiny shift, Bessel can calculate the distance to 61 Cygni, about 10 light years. The light we see tonight left that star a decade ago. Other measurements follow. Vega, 25 light years. Alpha Centauri, 4.3 light years, the closest star system to our own. Even the nearest stars are separated from us by distances that make the solar system look tiny. If you scaled the solar system down so that the Sun and Earth were 1 inch apart, the nearest star would be 4 miles away. The universe is unimaginably vast, and we've only just begun to grasp how vast it is, because Herschel has made another observation, another discovery that will eventually overturn everything again. He's been mapping the Milky Way, that luminous band of light that stretches across the sky. Using his powerful telescopes, he's resolved it into countless individual stars. The Milky Way isn't a cloud or a luminous mist. It's stars, millions of them, so numerous and distant that they blur together into a river of light. And Herschel notices something about the distribution of these stars. They're not scattered randomly. They seem to form a flattened disk, like a wheel viewed edge-on. Our sun appears to be embedded in this disk, and when we look toward the plane of the disk, we see the Milky Way, millions of stars stretching away into the distance. Herschel calls it the grindstone model of the Milky Way. We live inside a vast disk of stars, and the Milky Way is our view of this disk from the inside. But how big is this disk? How many stars does it contain? Herschel estimates hundreds of millions, maybe billions. He can't count them, there are too many, but he can estimate based on what he sees in his telescopes. And then he looks at fuzzy patches in the sky. Nebulae, they're called. Some resolve into clusters of stars when viewed through his telescopes, but others remain stubbornly fuzzy, even with his most powerful instruments. What are these nebulae? Are they clouds of glowing gas? Or are they, perhaps, other island universes, other disks of stars like our Milky Way, so distant that even the most powerful telescope can't resolve individual stars? Herschel isn't sure. He suspects some nebulae might be island universes, but he can't prove it. This question, what are the nebulae, will haunt astronomy for a century, and when it's finally answered, the universe will grow again, incomprehensibly larger,
stretching into distances that would have seemed like fantasy to the astronomers of the 18th century. But we're not there yet. Right now, in this moment, the universe...
Let's move to the American West now. The year is 1912. We're at Lowell Observatory in Flagstaff, Arizona, perched on a mesa with clear, dark skies that make it one of the best observing sites in the world. You're watching a man named Vesto Slipher work with a spectrograph, a device that splits light into its component wavelengths, creating a rainbow spectrum. But Slipher isn't looking at rainbows for their beauty. He's using them to make measurements that will transform our understanding of the cosmos. He's been studying the spectra of spiral nebulae, those fuzzy, spiral-shaped objects scattered across the sky. Some astronomers think they're clouds of gas in our own Milky Way. Others suspect they might be distant galaxies, island universes far beyond our own. Slipher has noticed something strange. The spectral lines of these nebulae are shifted. Remember learning about how every element produces characteristic lines in a spectrum? Hydrogen has specific lines, so does helium, oxygen. All the elements have their own unique fingerprints. But in these spiral nebulae, the spectral lines are in the wrong places. They're shifted toward the red end of the spectrum, red-shifted, as it comes to be called. This is because of something called the Doppler effect. When something emitting light moves away from you, the light waves get stretched out, shifted toward longer, redder wavelengths. When something moves toward you, the waves get compressed, shifted toward shorter, bluer wavelengths. Slipher measures the redshifts and calculates velocities, and the numbers are staggering. These spiral nebulae are moving away from us at speeds of hundreds, sometimes thousands of kilometers per second. Nothing in the Milky Way moves that fast. These objects can't be part of our galaxy. They must be separate galaxies, incredibly distant, receding from us at tremendous speeds. But why are they moving away? Why aren't some of them moving toward us? Slipher doesn't have an answer. He just has the data. The spiral nebulae are rushing away from us at enormous speeds. Let's jump ahead. It's 1923. We're at Mount Wilson Observatory in California, home to the largest telescope in the world, the 100-inch Hooker telescope, a monster of glass and steel that can peer deeper into space than any instrument before it. A quiet, methodical astronomer named Edwin Hubble is using this telescope to photograph the Andromeda Nebula, one of the brightest spiral nebulae in the sky. Night after night, he takes long exposure photographs, building up faint details invisible to the eye. And in these photographs, he notices something remarkable. Individual stars. The Andromeda Nebula isn't a nebula at all. It's a galaxy, a vast collection of stars so distant that they blur together into a faint smudge visible to the naked eye. But with the Hooker telescope, Hubble can resolve individual stars within it. And not just any stars. He finds variable stars, stars whose brightness changes in a regular rhythm, specifically Cepheid variable stars, whose period of variation is directly related to their absolute brightness. This gives Hubble a cosmic yardstick. By measuring how long it takes a Cepheid to complete one cycle of brightening and dimming, he can calculate its absolute brightness. And by comparing that to how bright it appears from Earth, he can calculate how far away it is. The calculation is straightforward. Light dims with the square of distance. If you know how bright something truly is, and you measure how bright it appears, simple mathematics gives you the distance. Hubble does the math, and the number that emerges is astounding. The Andromeda Galaxy is nearly 1 million light-years away. Modern measurements will later refine this to about 2.5 million light-years, but even Hubble's initial estimate is revolutionary. 1 million light-years. The light we see left Andromeda 1 million years ago, before humans existed, before our earliest hominid ancestors walked upright. The galaxy we're seeing tonight is the galaxy as it existed in the deep past. It's like traveling across an incomprehensible gulf of space and time to finally reach our eyes.
And if Andromeda is a separate galaxy, then all those other spiral nebulae must be galaxies too. Each one a vast collection of billions of stars, separated from us and from each other by millions of light years. The universe has grown again, not just a disk of stars, the Milky Way, but countless galaxies scattered through space. The Milky Way is just one galaxy among billions. But Hubble isn't done. He's about to make another discovery, one that will change everything again. He starts measuring distances to more galaxies, and he compares these distances to the velocity measurements Slipher made years earlier. And he sees a pattern. The farther away a galaxy is, the faster it's moving away from us. There's a direct relationship. Distance times some constant equals velocity. This relationship, now called Hubble's law, means something profound. The universe is expanding. Not just individual galaxies moving through static space, but space itself is expanding, carrying the galaxies along with it. The farther apart two galaxies are, the more space there is between them, and the faster that space is expanding, so the faster they move apart. It's like raisins in rising bread dough. As the dough expands, the raisins move apart. From any given raisin's perspective, all the other raisins seem to be moving away, and the farther away they are, the faster they're receding. Not because they're moving through the dough, but because the dough itself is expanding. This is what's happening to the universe. Space itself is expanding, carrying galaxies along with it. The implications are staggering. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and all the galaxies would be closer together. All the matter in the universe would be compressed into a smaller and smaller volume. How far back can you wind the clock? All the way back. Back to a moment when all the matter and energy in the universe occupied an infinitesimally small point. A moment of infinite density and temperature. A moment of beginning. The universe, it seems, has not existed forever. It had a birth, an origin point, a moment when time itself began. This idea, initially mocked as the Big Bang by a skeptical astronomer who thought it sounded ridiculous, will eventually become the foundation of modern cosmology, but we're not quite there yet. Right now, in the late 1920s and early 1930s, astronomers are still wrestling with what Hubble's discovery means. Is the universe really expanding? Could there be some other explanation for the redshifts? Some property of light we don't understand that makes distant galaxies appear to be moving away? But the evidence keeps accumulating. More distance measurements, more velocity measurements. The relationship holds. The universe is expanding. And if you accept that the universe is expanding, you have to accept something even stranger. The universe had a beginning. Not a local beginning, the formation of our solar system or our galaxy, but an absolute beginning. A moment before which there was nothing. No space, no time, no matter, no energy. Just nothing. And then, for reasons we don't yet understand, there was something. There was everything. The entire universe in an unimaginably hot, dense state, exploding outward, expanding, cooling, forming the cosmos we see today. It's a creation story, but not a mythological one, a scientific one, based on observation and mathematics and physical law. It's also a story that raises more questions than it answers. What caused the beginning? What came before it? Is before even a meaningful concept if time itself began at that moment? Will the universe expand forever, or will it eventually stop, collapse back on itself? These questions will occupy cosmologists for the rest of the 20th century and beyond, but we'll return to them later. Right now, let's pause and take stock of where we are in our story. We started with early humans beside a fire looking up at stars they knew intimately but didn't understand. We watched as Mesopotamian priests discovered order in the heavens, as Greek philosophers proposed that the earth moves, as Islamic scholars preserved and expanded ancient knowledge, as Copernicus, Kepler, and Galileo dismantled the old cosmos and built a new one. We saw Newton unify heaven and earth under one set of mathematical laws. We watched as Herschel discovered new planets and realized the vast distances between stars. We stood with Hubble as he discovered that our galaxy is just one among billions, and that the universe itself is expanding. Each discovery made the universe larger, older, stranger. Each answer raised new questions. Each generation of scientists peered deeper into the cosmos and found more wonder, more mystery, more beauty than the generation before. And we're not done yet, not even close. Because in the mid-20th century, scientists will make discoveries that make everything we've discussed so far seem simple by comparison. They'll discover that the universe is not just expanding, it began in an explosion of unimaginable power. They'll peer into the hearts of stars and discover where the elements come from.